All right, let's go. I'm going to go back in a minute. Oh, the AC theory one. Let's go and do that one now. It's a bit tedious, but it's important that you can do this. So number 3, a capacitor, a resistor, and an inductor are connected in series. So a capacitor, a resistor, and an inductor are connected in series to an AC source of C, R, L. Obtain an expression for the impedance of the circuit, so Z. How do we, can somebody suggest how we start off? No? What about a phasor diagram? If we're drawing a phasor diagram, then we need a reference vector. What do we normally take as the reference vector? Current. So we must write this down. Taking current as the in phase vector. Now what that means is we're comparing other vectors to the current. So that's our reference vector. So in a phasor diagram, we draw the current somewhere, normally horizontal. Now what do we know? We know that the voltage across a resistor is going to be in phase with the current. There's no phase difference. We know the voltage across a capacitor lags by 90 degrees, so that's VC as a vector, and VL going upwards, showing that there's a 180-degree phase difference between the voltage across the capacitor and the voltage across the inductor. I presume you remember, key thing I should point out, remember that in a normal circuit, a DC circuit, we just add the voltages across the components. So in line with Kirchhoff's law, we can say that if we are, I'll give you an example. Let's suppose we have 2 resistors connected to a battery. So the voltage across that is VR1, this is VR2, and the battery's voltage is V. Then in this DC case, we can say that V equals VR1 plus VR2. And that, indeed is Kirchhoff's law. The sum of the volts drops around any closed loop of a circuit is 0. However, when it comes to alternating current, we can't make use of that simple expression. We have to add our voltages vectorially. So what we're saying is that V that we supplied as a vector is VC plus VR plus VL, all added together as vectors. Now, phasor diagram, do you remember what a phasor diagram actually is? Another name. Can somebody give me another name for a phasor diagram? It's actually a more sensible name, I think. A rotating vector diagram, because these vectors rotate like the fingers of a clock, but by convention they rotate anti-clockwise. So if you were to this is sort of an aside to the question. You just need to, let's suppose we draw a graph here with time on the horizontal axis. And we'll take 2 vectors. We'll assume, we'll just take 2 vectors. We'll take the voltage across the inductor and the voltage across the resistor as our examples. Now at time 0, that's now, VR is on the axis, and VL now, at some time later, these vectors are all rotating around at the same frequency. So at some time later, pi by, yeah. Okay. Sometime later, when they've turned through 90 degrees, VR is now up here, and VL has gone back to 0. I'm muddling up the colours there. Okay, so the upshot is that that one's increased, and that one has decreased. And if we carry on, we truly get our 90-degree phase difference between the, in this case, the voltage across the inductor and the voltage across the resistor. So that's the point of a phasor diagram, that as it sweeps around, it generates sine waves. But from our point of view, the phasor diagram is important because we can resolve the vectors and do the calculation on the circuit. So we can see these are vectors in opposite directions, so the resultant vector of those two, if this is the longest, is going to be here, and this would be VL minus VC. Okay, now we can put a dotted line along, and there's the voltage we apply to the circuit. Okay, so getting back to the calculation now, we want the impedance of this circuit. So what can we say? We can say that V squared, the magnitude of the vector V squared, equals the magnitude of VL minus VC squared plus the magnitude of VR squared. From there, if we pull, these all have a current term in them, so if we pull out, where are we here? Yeah. The magnitude of V over the magnitude of I is going to, you could put a squared on it if you want, or we can just take the square root of this side, is going to be XL minus XC squared plus R squared. We're using there that voltage across the resistor is IR, and we've pulled the I out, it's over on the other side just for neatness. The voltage across the inductor is the current flowing through the inductor times the XL. What does XL stand for? XL is the
resonance.
Pardon?
Resonance.
No. No, it's a bit like impedance. Reactance. This is the reactance of the inductor, and this is the reactance of the capacitor. What is reactance? Any thoughts on what reactance is?
It's all it keeps balance the system when the AC current increases. It increases.
It may increase or it may decrease. It depends whether you're using an inductor or a capacitor. No, the simple definition, if I ask you in an exam, what is reactance? The simple definition, only about 4 or 5 words, frequency dependent resistance. In other words, resistance that changes with frequency. So that's the difference between these reactances and this thing we call resistance, because resistance is fixed with frequency. As we alter the frequency, the resistance doesn't alter. But this resistive property of a capacitor alters, and the resistive property of an inductor alters. That's why the key to a capacitor is it lets alternating current pass and blocks direct current. It's varying its capability to pass current depending on what frequency we supply to it. So, to cut a long story short, XL, that reactance, equals omega L, and XC equals omega C. Oh, sorry. XC does not. XC is 1 over omega C. That's the big difference between them. Here omega's on the top line and here omega's on the bottom line. So as we increase the frequency, remember omega is 2 pi f. So in the first one, as we increase the frequency, the reactance increases. But as we increase the frequency on the second one, the reactance decreases. So capacitors like to pass higher frequencies. The higher the frequency encountered, the easier it will pass through a capacitor. Whereas the opposite's true for an inductor. Okay, so we've got that expression down there. I also asked you to work out the phase angle. I'm going to have to cross. Can I get rid of some of this?